Please welcome Chris Colohan, who will tell us about blockchain consensus.
Hi there, my name is Chris Colohan, and I'm going to talk to you about blockchain consensus, which is the latest in a series of consensus algorithms that you guys have been studying in this class. When I use the term blockchain, it's actually really confusing to go out and read about what blockchain is, because there's so many people who are excited about it and writing about it and using this term in so many different ways, which mean different things. And blockchain can be everything from I'm going to make $1 million to a very specific data structure. So I'm going to try and be as precise as possible in my terminology in this talk. And I'm probably going to fail at times, and I apologize for that. But we'll give it a go. I also want to encourage you to interrupt me at any time during this and ask questions, because that way I get a better sense of what you guys already know and what you don't, because I haven't actually watched all of the previous lectures. I'm sorry about that. Watch some of them though. So let's start off, just quickly review what consensus is. You've already learned this, but let's assume you've got a bunch of computers run by their Byzantine general dictators. And you've got a data structure which you want replicated across these computers. Well, the way you do this is by achieving a consensus between the computers, and you can just replicate the data across a bunch of computers. Great, so that's the overly simplified view of consensus. How do you do it? Well, if you're designing a new system, you need to choose an algorithm which you're going to use in order to achieve consensus. And like good engineers, you always try and start with the simplest possible thing you can come up with. And you do some Google searching and you say, oh, two-phase commit. That's the way to do it. And you implement it and you discover, well, that works great in my system until one of my computers crashed and rebooted, and then, it added a bit of complexity, but it's okay. You can actually deal with fail restart behavior. But then one of your computers catches fire and goes away, and your whole system comes to a screaming halt, and you're like, what the heck just happened? And that's when you realize you need something more sophisticated, such as Paxos or Raft, which is able to deal with fail-stop behavior as long as you don't get too many of your machines failing. And so you're happy again. And then you get attacked by an evil hacker. Maybe one of your Byzantine generals turns into a devil, and that devil tries to actively subvert your consensus between your computers. And you're like, I actually need to change my system to tolerate this sort of subversive behavior. And so you go and you say, oh, fine, I'm going to implement a Byzantine fault tolerant solution. And so that's the next thing you do when you implement PBFT or some other complicated protocol, which can't really tolerate as many failures. It's a bit slower, but it can tolerate this Byzantine behavior. So that's kind of cool. And then you realize, wait a second, oh man, having my own pool of computers and running them and trying to achieve consensus, my application actually needs me to be able to add computers to the system over time, and also add computers that aren't mine. I need to have an open system where anyone can join at any time, anyone can leave at any time, and I achieve consensus between them. And so you go and you consult the theory and you say, oh, that's not possible. And it's actually, there have been many results throughout time of people proving that it's not possible to have an open system and achieve consensus amongst the computers, because you just don't have enough control over the computers to actually prove that you're going to get consensus in all the cases. And so what are you going to do? And that was thought to be impossible up until someone came up with blockchain consensus. And blockchain consensus is kind of cool because it lets us deal with getting a consensus amongst all of these computers, if computers are adding and dropping at random times, and if you don't control all the computers. But it has a problem, which is it's not really a consensus. It's kind of weird, and I'm going to get into more detail about how we've had to change the definition of consensus in order to achieve this supposed consensus amongst computers using the blockchain later in this talk. But as we go down through the stack of algorithms and we get to fancier and fancier ones, I just want to point out that every step we go down in this chain, we're getting something that's more general. It's also a little bit slower, perhaps requires more messages or even more time for other reasons than more messages. It's also more complicated. So your goal in designing a distributed system should be to try and start at the top of the stack and use a simpler approach if it's practical for your application, and only go to more complicated solutions if that's something you absolutely need in order to achieve whatever you're trying to build in your system. So let's go on and start off by defining what is a blockchain. But before I go on, I want to pause here and ask if we have any questions or if the audio isn't working or anything like that.
I think the audio is now working fine. Hopefully somebody will tell me if that's not the case. Yeah, so I have a question actually. So on the previous slide, so when we, so just to contextualize this a little bit for our class, so we didn't actually talk about two-phase commit at all. Um, so do you think that you could kind of like explain that very briefly and talk about how that's a little bit less general than a consensus protocol like Paxos?
Well, two-phase commit is simply the idea of you go through, it's actually similar to Paxos in that it has two phases, except you have a controller process that is trying to achieve consensus amongst a bunch of slaves, and you just send out one message saying, I want to achieve a consensus on such and such a transaction happening, say transaction A happening, you send that to all your nodes, and they either respond with a vote. They either say, yeah, okay, I'm willing to do that, or I'm not. And then you only proceed to the second phase, the commitment, if the first phase receives a majority of votes saying yes.
Mhm.
And so it's just really a way of just replicating the data across a bunch of computers in a way where you can either roll forward or roll backwards. And it comes from the database world, where you also do
Right,
this with two-phase locking.
right. But it does require you to have this controller.
Yes, it does require a
So,
controller. It's not fully distributed like Paxos.
right. So the word we tend to use for that in my class is decentralized. So Paxos is a decentralized algorithm. It's more general in that it's tolerant of that particular kind of failure.
Mhm.
But it's still not tolerant of Byzantine faults.
Oh, definitely
So
not.
so Paxos, so we discussed how Paxos behaves under omission faults, and we discussed how it behaves under crash faults, but we didn't talk about Byzantine faults because Paxos doesn't tolerate those. So that would be a whole new level of fault tolerance, which we haven't even discussed. And so what Chris is going to talk about is, so blockchain consensus actually can, in principle, tolerate Byzantine faults.
Some
Um,
of them, some of them.
yeah. So, or at least, yeah, a certain class of them. So, uh, but uh, but I think this is a good point that Chris is raising about how you don't necessarily need that kind of fault tolerance, and it depends on the assumptions that you're making about your system and the threat model, I suppose, the kinds of faults that you expect to experience.
Yeah, absolutely. Like, for example, it might be really tempting. Let's say you're building your own online game, say Fortnite. And Fortnite is a cool system because it very quickly replicates state amongst all of the players. And if you don't have very high speed state replication amongst all the players, the game is just no fun to play. And so it's really tempting to say, gosh, wouldn't it be nice to build this in a fully distributed manner where we don't need any servers at all and all the players can just talk in a peer-to-peer fashion and have the game run? Except all of the solutions that we know of for doing that sort of state replication are slow.
Mm.
And they would make the game horrible to play if we tried to do it on the blockchain, for example, because you'd only be able to fire one bullet every 10 minutes. And then your bullet might not actually fire because it might come back at you 20 minutes later. So it's not the be all and end all solution. So before we can talk about how to achieve consensus on a blockchain, we need to define what a blockchain is. And so I'm going to be very specific in this talk. When I say blockchain, I'm talking about the blockchain data structure. And so what is a blockchain data structure? Well, let's say you've got some data and you just want to put it on a blockchain. So what do? You carve off a piece of that data and you make a block of data. And so it's just a subset of your data is a block, and you can choose whatever block size you want. In Bitcoin, I think they choose a block size of 1 megabyte, and they may have expanded it to 2 megabytes. Doesn't matter. It's just a fixed size chunk of data. And like any good data structure, you need some metadata as well. So you put some header on it. And for our first block, we'll just leave the headers empty. Then when we create a second block, on the top of that, in the header, what we do is we put the hash of the first block of data. And that's what chains the blocks together. And that's why it's called a blockchain, is because every time you add some more data, it points to the previous data, not through a pointer, but through a hash of the entire contents of the previous block. And when we use this hash, we actually have to use a special type of hashing function. We can't just use like sum all the bits and XOR them or whatever we want. We have to use something that's called a cryptographic hash. And the cryptographic hash that happens to be used by Bitcoin is SHA-256. But the important property of this cryptographic hash is it has to be hard to fake. You can't just go and change some of your data on your first block and have the same hash on the second block pointing back at it, because then it doesn't have the properties that are interesting to us as we build the blockchain. And then as we add more data, we just add more and more blocks using this technique. So that's what a blockchain is. And why is it that a useful data structure? Well, the thing that makes it useful is that if you know the last block of data, or even just the hash of the last block of data, you can then validate that none of your data structure has been corrupted. And so that means that if you can successfully find some way of getting just the last block of data in this entire data structure, which may be megabytes or gigabytes in size, you can then get the other blocks from anyone in the world. Evil players, good players, nice people, mean people, and you know that your data structure hasn't been corrupted. You have a valid, correct copy of the data structure. And this is the chain of trust that you get from these hash values. So that's kind of cool. So we can just, validate the whole data structure. Great. Now, the Bitcoin blockchain is exactly this. It's just a bunch of blocks of data that have been chained through these hash values. But a problem that the Bitcoin data structure has is it's, big. There are a lot of transactions. It goes back to the very beginning of Bitcoin, and every transaction that someone does gets an entry in one of these blocks. And they keep on adding more and more blocks, and eventually, too much. I tried looking it up, and there are various estimates of the current size of the Bitcoin data structure. It's something like, I think it was 300 gigs last time I found someone that measured it. I'm sure it's bigger now, but if you launched your own Bitcoin client on your laptop, you probably don't want to have to download 300 gigs of data before you do your first transaction, because that would be kind of annoying. But you do need to download the Bitcoin blockchain if you want to validate all of the transactions that lead up to it. And you want to prove, for example, that someone who sent you money actually has the money to send you.
So Chris, there's a question in chat right now, which is how exactly does that validation process work? How would you validate that the last block in the chain is correct?
Well, that's the key to the whole thing, which is you do it by running a consensus algorithm, the blockchain consensus, in order to get that block replicated to your computer successfully and trust that is correct. But the short answer is if you know a lot of nodes in the Bitcoin universe that are doing mining, if you ask a bunch of them for the latest hash and they all agree, then you're good on the latest block. And if they disagree, then you just don't trust it so much. And that's yeah. And so establishing that trust and knowing that you've received enough information to actually trust is correct is part of the leap of faith that's involved in Bitcoin, I would say. Mm-hmm. And so we'll get into faith issues later, because this is partially a technical talk and partly a religion discussion. So we have too much data. And so the question is, can we make it so that it's smaller, so we don't have to download as much data to our computer in order to do our first Bitcoin transaction? The answer is yes. We use this technology, which I'm told you've discussed before, which is Merkle Trees. If in our blocks in the blockchain, we do not store all of the transaction data, but instead in each block, we make it really small and just store a Merkle hash in it, then our blocks are kind of tiny. And so we can download the whole blockchain without overwhelming your average laptop or desktop computer. And so what the Merkle tree is, a quick review, is you take all the transaction data and you divide it up into transactions at the leaves of a tree. And then for every 2 transactions, you compute the hash of those transactions, and that's a subtree hash. Then you compute the hash of those subtree hashes, and that's the next level subtree hash, and so on, up until you get the Merkle hash at the top of the tree. And so why does this help with the amount of data we have to download? Well, it turns out if you don't want to download all the transactions that involve people's wallets who you're not transacting with, you just don't download that data at all. And instead, you just download the data for the transactions you care about, and then you can validate that they are correct by recomputing the subtree hashes above those, and then recomputing the subtree hash above that, and then recomputing the subtree hash. And now we've got the hash on a block that is on our blockchain. And so we can do the chain validation that we talked about a second ago, just marching up the blockchain until we get to the one head node that for who knows what reason we trust. And so we've now validated that the whole thing is valid, assuming we got the right head node. Does that make sense? And so this is really not necessary to understand the correct operation of the blockchain, but it's a really cool performance hack, this Merkle tree, because it allows us to save a lot of space in terms of what data we need to download to do a particular set of transactions. So that is the blockchain. So it turns out that understanding the blockchain is really simple, and all this stuff which you read online about the complexity of the blockchain stuff, it's bogus, because they're talking about the blockchain in terms of the entire ecosystem and not just the simplicity of the data structure. The data structure itself, there's not that much complexity to it.
The data structure itself reminds me of Git, actually.
Yes. Yeah, no, it's pretty similar. Well, Git is just reverse diffing. It's just a log. And blockchain transaction log is just another form of log as well. Mm-hmm. And similarly, they use hashes in order to identify objects in it. Mm-hmm. So yeah, no, it's very similar. Let's talk about consensus. So I've mentioned this already. If you're trying to choose a consensus algorithm, you should just use Paxos, Raft, or PBFT, because they are better algorithms. They're faster, and we're going to harp on this a lot. And it turns out that when you look at the world of blockchains, people use blockchain as this magical way of getting venture capital funding, but you can divide it really into two worlds. And one world is the world of private blockchains. These are the people talking about, oh, I'm going to use a blockchain to validate that the corn you got on your table comes from the farm field, which you think it is. And they are usually talking about a private blockchain where you've got multiple parties participating, but they're all cooperating parties who you sort of trust to only set up a fixed set of servers and not necessarily have random Joe Q public join into the blockchain and add nodes to your blockchain. And these private blockchains, the thing they care about is that your blockchain was replicated between participants. If any of those participants tries to suddenly turn evil, the other participants can say, oh, no, I've validated my blockchain and you tried to change a transaction in the past and that's bad. And so they're just relying on the properties of the blockchain data structure, but they don't care at all about a public consensus where nodes can enter and leave the system at any time. And so those people are much better served by using a blockchain data structure, but using a traditional consensus algorithm such as PBFT for replicating their data between machines. And they're going to do that because there's no way they are going to spend all of the electricity and time on this public consensus algorithm, because it's a waste of effort for them.
I do want to point out one thing here, which is, so this thing about any machine joining or leaving at any time is very interesting because, think of Paxos, for instance. So in order for Paxos to work, you have to know ahead of time what a majority is, right? And so if there are machines joining and leaving, then the answer to that question can change, right? So this idea of dynamic membership is actually something that Paxos doesn't work very well with at all.
You mean it doesn't work at all with?
I mean, there are flavors of Paxos, right? Like people have tried to invent. So actually, my colleague here at UCSD, Faisal Nawab, has something called the dPaxos, which is supposed to work under dynamic membership, I believe. But I think it ends up looking a lot more like. Well, I hesitate to put words in his mouth because I don't know how it works, but I think it ends up looking more like what the consensus protocol that Bitcoin uses looks like. So this is one of those one of those advantages that you gain by using this more complex consensus protocol. You get the ability to have this dynamic membership in the number of nodes that you're trying to achieve consensus among.
Yeah, this is actually something that is key here, which is most consensus protocols, other than this one, have somewhere in them buried the concept of majority. And you can only take an action once you achieve majority, but that involves you have to know what a majority is. And this Bitcoin public consensus doesn't have a concept of majority because you have no idea how many nodes are participating. And you only have a rough estimate of it, and you can't really achieve a majority anywhere. And so I'd actually be interested in looking at the Paxos you're describing and see if it actually somehow does away with the concept of majority, or has some form of rate limiting admission control or something, so that on each round you know what a majority is defined to be, or something like that.
Yeah, he's got a Sigmod paper about it. Let me share that.
Sounds cool. I'm not going to read it now.
Sure.
I'll get it after. Bitcoin, on the other hand, is a public blockchain. Any machine can join or leave at any time. And so this means that there's this interesting class of attacks, which is, since if we did rely on a majority of machines for any concept of that, an attacker could just create an infinite number of virtual machines and overwhelm anything we come up with. And so that's why we can't rely on a majority, is because of the existence of virtual machines. We don't have a good way of tying users to a physical resource, which they only have a limited ability to get. So what can you do? Well, we need to do something different. We need a new consensus algorithm. So let's invent it. And so the way I'm going to explain this is we're just going to invent the consensus algorithm from scratch, one step at a time, identify the problems, and then add to it and see what we can come up with. So what are requirements? Every time we add a block to the blockchain, it needs to eventually be consistently replicated to all of the other nodes in the system. All the other good nodes. Any node that's turned evil, we don't care about, because evil nodes can do anything. The newer blocks have to point to this block. So we have to actually create a chain and not a bush or a tree of blocks, because that's not useful to us. Nodes should be allowed to join or leave at any time, while maintaining consensus amongst the nodes that are still in the system, and also without causing a deadlock by having this happen. And to be clear, we want nodes to be able to join or leave at any time, but we can't have something like all the nodes leave at once, because then we don't have a system left, or an infinite number of nodes join right now, because, well, it has to be within some realm of reason. And I'm being very hand-wavy on the definition of that, because there isn't a strict formal definition, sorry. And it has to be network partition tolerant. And so I'm told you've talked about network partitions. If your network breaks, you now have two distributed systems where you once had one. And so each half of your partition has to be able to keep on working and should be able to form a consensus. And when the partition heals, so does the consensus. So we might have two consensuses that merge into a single one. And this is weird. I just want to really emphasize it. This is weird. This is not what consensus means when you're doing Paxos or PBFT or two-phase commit or one of the other protocols. Consensus in those cases means you have a commit point. Actually, I'll go on the next slide. Once you have a commit point, you've achieved consensus. It's not going to change. You're done, full stop. Blockchain, on the other hand, with this consensus, is you get to a point where you say, at this point, we probably agree. And at this later point, we're probably more sure that we agree, but we're never going to be 100% sure, but it should be good enough for, your bank account balance, right? And so if a computing superpower happens to zoom in and totally mess with your blockchain, well, the whole system could be hosed and it might change your bank account balance, but why would they? So yeah, we're all good, right? And so we've changed the definition of consensus to being there's a firm point in the algorithm where you know the answer for sure, to one where there's a firm point in the algorithm where with very high probability, and you can make that probability almost arbitrarily high, but it's only with very high probability that you've achieved consensus. So I hope you're good with that, because otherwise you're not going to be using blockchain consensus. So let's start building our algorithm now that we know what the requirements are. Let's assume that we've got 3 computers and they're trying to achieve consensus. And computer 1 decides to add a block to the blockchain. Cool, so it's added a block, and then it tells its friends, it tells computer 2, and then it tells computer 3, and we've replicated it, and we've achieved consensus. Woohoo! Our algorithm's working so far. When you generate a block, you tell another computer about it, and they keep a copy of your block. Simple algorithm so far. We add more blocks. Well, computer 1 adds another block, it gets replicated to the other computers. Okay. And we just keep on building it. Oh, what happens when computer 1 and computer 3 at the same time decide that they want to add blocks to their blockchain? Well, they follow the algorithm as I've defined it so far. Add a block, tell your friends. So they tell computer 2, which says, oh, now I've got 2 blocks that come after the second block. And then they tell their friends, and they tell their friends, and now, oh, we've achieved consensus. We have 2 blockchains. This is called a fork. And this is not good news, for your blockchain when you have a fork, because we wanted a chain and not a tree or a bush. So the question then becomes, we need to add another step to our algorithm, which is, if a fork happens, how do we resolve it? And like all good distributed systems, the best way to resolve something is just flip a coin, pick randomly. So let's do that. Each computer, if it wants to add another block, it picks randomly what block it will build off of based on the longest branch that it sees at that time. So computer 1 picks randomly, happens to pick the one on the right, adds another block, and replicates computer 2, which then replicates computer 3, and now our fork is resolved. It's resolved because now there is a single longest chain in this block, and so all future blocks will be added to that longest chain. Great. And we keep on adding blocks, and we're happy. Okay, so our algorithm now has 2 steps. One is, when you add a block, you just add a block to the blockchain and tell your friends. The second is, if you're not sure where the parent of that block is, pick randomly amongst the longest blockchains that you observe. Okay, so that leads to a case where we might have Livelock. In this case, computer 1 picks randomly, happens to pick the node on the left, adds a block. Computer 3 at the same time picks randomly, happens to pick the one on the right, and now both computer 1 and computer 3 are really clear. They both have a longest blockchain that they should add future blocks to. And so they do. They just keep on adding blocks and compounding the mistake. Computer 2 gradually catches up as the network messages reach it. But, this can go on forever. Both computer 1 and computer 3 can keep on adding blocks. They're totally convinced they're right because the algorithm says they're right. And all the other computers are just like, I don't know which blockchain is correct, and we never achieve consensus. And just keep on going, and that's no good. And eventually everything replicates, and eventually, well, no, it doesn't, because we keep on adding more blocks.
So is this what the blockchain community refers to as a fork?
Yes.
Okay.
Yeah, this is what the blockchain community calls a fork, when you happen to have blocks that were added to 2 different blockchains at the same time. Mm-hmm. And you want your fork to resolve, because if your fork is unresolved, mm-hmm. then you've got transactions that say, I paid Lindsay money and I also paid Bob money, but I gave them the same dollar. Mm-hmm. And that means you've invented money, and that's not good for current currency. And so, yeah, you want your algorithm to, if a fork happens, for it to be resolved as quickly as possible. So let's talk about that. Why do we have this Livelock? And I'm going to ask the class this. What's the fundamental reason why our algorithm, as we defined it so far, is Livelocking? And I don't know if if answers will go through you, Lindsay, or if people can unmute and answer, or.
Yeah, so so there are already some people typing
okay.
In chat.
Sounds good.
So there's also a slight delay on Twitch, so.
Which makes it more fun to ask questions like this.
Yes. Well, okay, so one person suggests concurrency.
Absolutely. If we didn't have concurrency, we wouldn't ever have Livelock. But in spite of, so what kind of concurrency, or what is the aspect of this concurrency that's causing us to have this trouble?
And timing.
Timing?
Yeah.
What about the timing? Wow, this is so much easier when you're live.
Right, right. So something about schedule non-determinism, perhaps?
That probably helps. But the fundamental issue that's going on here is that we can add blocks on a node much faster than we can learn about other nodes that have added blocks. The time it takes for me to add something to a data structure is really short, but the time it takes for me to learn about something that happened on the other side of the planet is really long. And therefore, as long as we can keep on adding stuff to what we think is the longest chain faster than we can learn about someone else who might have created a longer chain, we're hosed. This algorithm will never work. And so the solution to this is to just slow the system down. Why don't we just add some artificial delays into the system? Make it so that we can't add blocks faster than we can learn about other people's blocks. And so that's what we do in the blockchain. In blockchain consensus, I should say. I should use my terminology correct. We just insert a random timeout. Make sure that that timeout is long enough that we're likely to have learned about other people's block additions before we go and add a block ourselves. So let's see how that works out. So we go and we start a timer on all of our computers, and we pick a random timeout. And eventually, one of those timers expires. So on computer 1, the timer happens to have expired first because it got lucky. And so it adds a block. And then what it does is it tries to starts a timer again because it has to wait some more before we can add a second block. And it communicates with all the other computers it knows about that block. And that communication arrives, luckily, before the timeout expired on computer 2. And so it starts a new timer after adding that block. And similarly with computer 3. And we've achieved consensus. Our fork has been resolved because now all the computers participating in the system have learned about the new block, and they're, have a new timeout going.
So it's perhaps worth pointing out that something kind of related could happen with Paxos if you have multiple proposers and the proposers' messages to the acceptors are interleaving in just a way that makes it so you can never get a majority of acceptors to accept. So when that happens, one way to fight that is to have different lengths of timeouts on the different proposers so that they're not always incorrectly intersecting with each other. And so this idea of random timeout length before a proposer tries again could help stop you from having this situation of dueling proposers.
Yeah, this is such a common concept that, like, at least when I was at Google, part of the standard library that everyone used is there's a random timeout function.
Mm-hmm.
You've got mutexes and you've got random timeouts, the two tricks to solving all your concurrency problems, right? You put them in, put in a bunch of them, you slow your program down, and suddenly it's mostly works. Don't do that. No, actually. Be very careful about where you use both those tools, but sometimes people aren't so careful. And so, it works really well, right? So then you ask yourself, how do you choose your timeout? And this is where the deep mathematics and science and modeling of blockchain comes in. Oh, no, actually, sorry, I take it back. Okay. So you sort of guess. What you really want is if your timeout is too long, your system will be too slow. If your timeout is too short, your system will be too slow. And that's sort of counterintuitive. The reason it'll be too slow if your timeout is too long is because your computers will be just sitting there doing nothing for too long. And doing nothing is not fast. If your timeout is too short, your system will be constantly adding blocks, constantly generating forks as the various nodes can't communicate with each other fast enough. And it will take too long before one of those forks eventually maybe gets resolved. Or you might get in a Livelock situation where it's never resolved. And that would be infinitely long, so that's kind of slow. And so you have to have your system try and guess where it is in that spectrum and pick a reasonable value. And the conservative thing to do is just pick out timeouts that are too long. And then you always know where you are and you're happy. So that's one problem solved, which is forks. We can solve them with random timers. So let's see what other problems we have in our algorithm. Let's talk about network partitions. So we have our 3 computers, they're working along, building the blockchain, and a network partition happens. Suddenly, computer 1 and computer 2 can talk to each other, but they can't talk to computer 3. And computer 3 also can't talk to computer 1 and computer 2. So what do? Well, you keep on running the algorithm. And computer 1 happens to add a block because its timer expired. And it communicates it to other computers, computer 2, and it never learns about it on computer 3. Well, computer 3's timer expired because its timer was never reset because it never learned about this block. And it adds its own blocks. And so you just keep on adding blocks. But something to notice is that there are more timers on the left side of this diagram with computer 1 and computer 2 than there are on the right side. So the probability of one of those timers expiring faster is much higher on the left side, it's twice as high, as on the right side. And so therefore, it's going to more than likely grow faster than the right side because there happen to be more computers on that side of the partition. And usually when you get a network partition, it isn't a nice even split down the middle, especially in a global network. It's usually like one data center happens to have fallen off the network, or one country's network cables was subject to backhoe fade, or someone's shotgun shell in the middle of the woods or something. That's actually an entire another topic of what causes network failures in long distance networks. It's amazing the stories you hear of well, it's mostly backhoes, but you also hear about bullets and avalanches, which are kind of cool.
I believe we discussed backhoes and tornadoes in this class so far.
Problem is I don't know what stories are public and what ones are not. But I can tell you, one of the most epic stories I heard was an avalanche in the Cascades that cut off an entire data center for more than a week, I believe it was, because it was just too dangerous to go in and fix the cable because the snow was unstable. So anyways, whoever's on the bigger side of your partition will go faster. And because of that, they will get more blocks on there, which means that when the partition is resolved, our algorithm just continues to work. The data is replicated, and then computer 3 suddenly realizes, oh, I was wrong. The consensus I thought we had was wrong. And I'll just start working on the longer side of the fork, and we're all happy again now. Even though while the partition was happening, you might have gone and told your customers, oh, we've achieved consensus and I've given you your money. And then you're like, oh, I got to claw it back, So you probably, in a reasonable implementation of a Bitcoin client, before taking any actual real world results, such as cashing out money, you might want to have a check to make sure that you have good network connectivity to a majority of the nodes in the world. Because otherwise, you could lose a lot of money. And that's actually, issues like this is one of the reasons why it's often so easy to put money into a cryptocurrency, but hard to get it out, because the people who take the money out are taking a real risk of something went wrong, which their code failed to detect. And therefore, they're going to lose real money when they try and give you back your fake money. Sorry, fake, virtual money.
So a couple of questions in chat. So here's one that this might be really specific to Bitcoin, but I think it might go back to the discussion of forks. So the question was about the splitting of Bitcoin to Bitcoin Cash, Bitcoin SV, and regular Bitcoin, and what happens there. So I don't know the answer to this question at all, because I don't know anything about Bitcoin. So is this is this like a Bitcoin specific question, or is this something that that you're qualified to answer, Chris, or what do you think?
I would claim I'm not entirely qualified to answer that question, because I'm not an expert in cryptocurrencies. But when you do have a fork into multiple algorithms or multiple cryptocurrencies, basically you need to get all the participants to agree that they're going to fork, at least the ones that are going to do the new currency. And if you don't, well, then it just doesn't happen, because you never get the majority and you don't get consensus across all of your nodes.
Okay, I wasn't sure if this was a question about forking or if this was some other Bitcoin related question. So
forking has two, like all great terms, it has two meanings in the cryptocurrency community. One is where you are forking a currency. You have the US dollar and you want to fork it into the new and the old US dollar, and you can't trade between those two new currencies. And I believe that's what this question is asking about.
I see.
Which is the politics of taking what was a single currency and splitting it into multiple currencies, with different rules of the game for the new multiple currencies. Maybe different algorithms or different trading rules or whatever. When I'm talking about forking this talk, and what I'm talking about is the very specific short-term, two different nodes happen to have come to different consensuses, and then later they needed to merge their worldview into a single worldview again, so that they can only have a single blockchain. And so that's what this example in the network partition is doing.
Okay.
Did you have another question queued up, you said?
Yeah, so there's one here. Let's see if I can summarize the question. So, so after a timer expires, so the question is, when a process's timer expires, does it randomly choose a block? I'm not sure if I understand the question, actually. So I'm not sure if I can rephrase it properly.
So there are multiple questions that might be buried in there. One is, when the timer expires, does it randomly choose where to add the block, what parent block to point it to? And the answer is, if there's a single longest chain as viewed by this node, no, it's not random. It picks the longest chain. If there's two or more chains which have the same length, which it needs to pick from, then yes, it does randomly pick a parent node. But the other question you might ask is, how do I decide what transactions go into a block? And that's a very loaded question. It depends on the cryptocurrency, what a miner chooses. It might be, for example, you could say that when you send a transaction to a mining node saying, I want to be added into a block in the blockchain, you accompany in your transaction, say, not only am I giving Lindsay $5, I'm also going to give whoever happens to add this to the blockchain a tip of 25 cents for doing the nice work for me. And so they might sort all of their requested transactions by the tips and take the ones that make them the most money first. And so that's one mechanism that's used in order to decide which transactions get put into a block. But that's not really the topic of what I'm talking about today, because yeah, that's not part of the consensus. That's part of the economics of the system and how transactions occur. Any other questions?
That's it for now.
Sweet, I will move on. Okay, so yeah, great. So what's left? We've covered how to create a blockchain. We've covered how to deal with forks. We've covered how to deal with network partitions. And choosing a timeout value, we've only roughly covered. What you basically do is you do it empirically. You basically say if the new blocks are arriving too quickly and we're getting too many live blocks, you slow down. And Bitcoin actually does this by every 14 days. It looks at the average transaction rate over the past 14 days, and then it adjusts its timeout such that one transaction is expected to occur every 10 minutes, which is, to me, that sounds insane, but it's what they choose to do, which is one block added every 10 minutes. That's really safe because hopefully the whole network can communicate any changes between itself in 10 minutes successfully. Okay, so that's what Bitcoin does. But then there's one other issue, which I've sort of ignored so far, which is what if a computer cheats? What if one of your computers lies about its timer expiring first? That's really bad, because it means that one node could earn all the tips, as I mentioned a second ago, by adding all the transactions to the blockchain, and no one else will give it a chance to add any blocks. So how do we make a timer that can't be cheated? And that is the key thing to this entire public consensus. And so how do you make a cheat-resistant timer? Well, there's the elegant and cool way, which of course we don't do, which is we use cryptography, aka the way to do this using crypto techniques is trusted computing module. Most of the computers participating in the blockchain happen to have something like Intel SGX in their CPU, a little enclave where you can do your trusted computing. And it's really simple code to say inside the trusted computer, wait a random period of time, and then spit out a little token that says you are now allowed to do whatever the next action is. And there actually is a blockchain that's been designed around that concept. It's the Intel Sawtooth blockchain. And it works great as long as you trust the trusted computing module to always do the right thing. And sadly, there are two holes in this. One is you have to trust Intel to not leak their private keys and their root of trust for the trusted computing module and not to want to corrupt your blockchain. And whether or not you trust Intel, well, I'd argue you probably already do trust Intel because you're running on their CPUs anyways, so maybe it's not that much of a stretch to trust Intel. But the other thing you're trusting is you're trusting the future. You're trusting that future hackers don't suddenly find a way of a new hack for whatever the latest patched version of the trusted computing module is. And historically, that hasn't been a fantastic bet because our darn researchers are just too good at finding new ways of hacking these trusted computing modules. And so no one has made a large long-term bet on a blockchain that's based on this simply because it's not historically proven to be a good bet. And I would love it if we made these modules so good that we could trust them for something as critical as this, but it just hasn't happened yet. And so there's always hope for the future. So the elegant way doesn't work. Let's go to brute force, aka physics. And so this is the way that Bitcoin actually does it. And it's this. If you want to create a block, before anyone else will accept your block as a valid block being added to the blockchain, you have to solve a math problem. And you need to prove to other people that you've solved that math problem. And so the way you do that is you solve the math problem, and then you include the solution in the block headers of the block you give to everyone else, so that they can verify that you actually did solve this math problem and that you did something that takes a long time to do, presumably as long as the timeout that you were aiming for. And also for this to work, verifying that you solved the math problem, that for me to verify that you solved the math problem should be really easy and fast, because otherwise you could waste a bunch of my time, which I'd rather be spending trying to solve my own math problems. So how is this done? It's called proof of work, and the way it works is like this. Remember our blockchain data structure and how I said there was a cryptographic hash on each block that contained the hash of the prior block? Well, when we create a block, those headers don't just contain a cryptographic hash. They contain a number of things, but the other key thing they contain is a nonce. And so what's a nonce? A nonce is just an arbitrary number. You get to pick what your nonce is, and your goal when you pick a nonce is to make it so that the hash of the block that you've just generated has leading zeros. How many zeros do you say? Well, the number of zeros is the parameter that the Bitcoin algorithm chooses to make it so that you can't possibly generate more than 6 blocks per hour for the whole global network. So everyone independently using the same algorithm looking at the rate of new blocks coming in can determine how many leading zeros you need in your nonce for other people to accept it. Sorry, not in your nonce, in your hash for other people to accept it. And so then, since everyone knows that, well, right now I need 4 zeros for other people to actually accept a block when I ship it to them, so I need to come up with some random number that means that the hash of the block that I just generated happens to have 4 leading zeros. How hard is that? Well, remember, I said it's a cryptographically secure hash. And because it's a cryptographically secure hash, there is no algorithm that can tell me what nonce I should pick in order to get 4 leading zeros. The only way to figure this out is to guess, compute the hash, get it wrong, guess again, compute the hash, get it wrong. And so the algorithm proof of work is how quickly can you guess random nonces, recompute hashes, and see if you eventually get lucky, win the lottery, and have the right number of zeros at the beginning of your hash. So you just burn power, waste electricity, and eventually you might be able to add a block to the blockchain. Okay, so that's it. That is Bitcoin consensus. We just reinvented it from scratch by going through and knocking down the dominoes, solving the problems that with our previous algorithms one by one. And so it combines 2 things. One is the blockchain data structure, and it combines that with a proof of work race to add blocks, where it's just using proof of work as a randomized timer. So this brings up an obvious question, which is, should you use Bitcoin consensus for your system? So let's try putting some numbers on this. Throughput, Paxos, Raft, PBFT, you should be able to get easily in a decent solution, thousands of transactions per second. Bitcoin, on the other hand, in a decent solution, get 3 to 7 transactions per second if you look at the average transaction size and the fact that only 1 block is added every 10 minutes. Huh. Okay, let's look at another number. That didn't look too pretty. Latency. Paxos, Raft, and PBFT, if you're unlucky, global network latency is less than a second, so you can add a transaction to the system in a second. Bitcoin, before you're actually mostly sure that consensus has been achieved and you want to return to your customer a result of, yes, you've successfully transacted, it's about an hour. Because most people claim that you want to wait until at least 5 more blocks after your block is added to the blockchain before you're sure you're not on a fork.
And even that is not a guarantee, right?
Oh, it's not a guarantee, but it's considered to be good enough. Mm-hmm. Maybe, probably. Good enough to exchange money on. Mm-hmm. And so, yeah, it's a bit of a latency difference. Okay, well, let's look at a different metric because, you know, this makes Bitcoin look bad, so let's ignore that. Okay, so energy usage. Paxos, Raft, PBFT, I did some back-of-the-envelope compilation and said, well, it takes about 1.4 milliwatt hours to do a transaction, so, you know, that's kind of, you know, you're wasting energy. Oh my God, Bitcoin, what have you done? Bitcoin uses a huge amount of energy per transaction by comparison. So you say, okay, fine, this is all a horrible mess, but can we fix this? And it turns out, yeah, we can fix this. Here, let me turn down the volume of my cell phone because it's ringing in my pocket. We can just use bigger blocks, right? Amortize the cost over, put more transactions per block, and we fixed a lot of the throughput issue. Or even better than that, instead of waiting 10 minutes for every block, how about every 10 minutes we win the proof of work race? And that just gives me the honor and the privilege to add more blocks, as many as I want for the next 10 minutes until someone else wins the race. And that's actually what the a proposal called Bitcoin NG proposes, is that winning the proof of work race doesn't give you the ability to add 1 block. It gives you the ability to just keep on adding blocks until someone else wins. And so that solves the throughput problem. It decreases the latency to your block getting on the blockchain, although not necessarily the latency until your block is trusted to be stable on the blockchain. And so we can solve the throughput problem pretty easily, assuming we could get those changes through on the Bitcoin system.
Mhm.
We can also decrease the energy usage easily by switching to another proposal, which is proof of stake, where instead of having to win a timeout race, what you do is, in order to get the honor of adding a block to the blockchain, you prove that using that you have the most money in the blockchain right now. And it doesn't firmly go to the person with the most money, because that would mean just one person would constantly be adding blocks. It's amongst the amount of money you have determines the probability of whether it's your turn or not to add a block to the blockchain. And it's deterministic so that everyone knows whose turn it is next based on how much money everyone has on the blockchain right now. So that works, right? So why doesn't Bitcoin do this? And there are a few reasons. One is currencies rely on trust. And quite frankly, if you make something more complicated to understand, fewer people will trust it. And because fewer people trust it, they don't necessarily agree to changing what's currently working right now. And if you can't get everyone to agree at exactly the same time to change Bitcoin, it doesn't change, because people keep on doing the old thing and transacting on the old system. And part of this is, I would argue, a political problem, because the people who really like Bitcoin and really like cryptocurrencies are the exact type of people who are not inclined to put a lot of trust in the good intentions of other people. And so in order to make a change in this system, you have to get them to all trust each other enough to actually make a change, which is hard and proven to be almost impossible in most cases. So it just hasn't happened. Okay, so theoretically we can fix it. In practice, it hasn't been successfully fixed on existing popular blockchains. Of course, there are a zillion and one not so popular blockchains where they do everything in all possible combinations of stuff. So I'm going to argue that the performance issues can technically be fixed. Whether they can be politically fixed is another discussion. But you still need other things if you want to generate your own blockchain consensus. You need a cult leader, because you need someone inspiring enough to get a whole bunch of people to join you. Because if you don't have a lot of miners and a lot of people working on your blockchain, you don't get the security guarantees of, oh yeah, your data will never go away because you have enough replicas. Well, if you don't have enough replicas, you don't have enough replicas. You don't get the security guarantees of no one can possibly ever corrupt your history because everyone agrees on what history is. Well, if you don't have everyone agreeing on the history because most people aren't participating, a large group of people can join you, and you're hosed. It's sort of like, actually, I was watching a back episode of a show called The West Wing last night, and a politician proposed that, you know what, you aren't seriously good about gun control. And they're like, what do you mean? He's like, well, if you wanted to get rid of the NRA, it's really easy. You get all the people who are who are for gun control to join the NRA. And suddenly you've got 3 million new members of the NRA. They only have 2 million. So you just vote everyone out of office and you're done. And it's like, well, okay, that's an approach if you could actually get 3 million people to all march in the same direction and do something silly as that. But it's a real possibility with computers, because it's easy for one person to control a large number of computers and get them to do something evil. You also need to make sure you've hired a cryptographer, or better yet, a whole team of cryptographers to make sure you haven't messed up. Because if you have any flaws at all in either your algorithm or your implementation of it, your cryptocurrency might be dead in the water. And you also, well, this is actually what I think is the hardest part of the whole thing. You need some way of paying your block miners. If your block miners, if their interest in preserving the integrity of your blockchain isn't aligned with yours, then they are not going to do it. If they're not making money off of it, they're not going to do an expensive proof of work algorithm, which costs a lot of electricity to run. And so if you're building an application that doesn't include some form of payment with money, reputation points, something that gets people wanting to do the right thing, you don't have a good application for blockchain consensus, as far as I can tell. Because this algorithm really relies on the fact that in order to get the desired outcome, you need to have aligned interests amongst the participants. And they have to be aligned in a way which they want to stay aligned, because otherwise they have something to lose. And so I want blockchain consensus to win, just because there's so many cool applications that you can do when you allow a public consensus amongst computers. But I've not really seen, personally, compelling cases for applications that weren't, oh, and then you trade some money. There has to be some financial aspect. Otherwise, I haven't seen anything that's compelling that I think will really, truly work well, sadly. So conclusion here is, so should you use it? Well, if you don't have a strong need for a public consensus, it's a pain in the neck, so don't do it. Just use Paxos or PBFT and create your own private blockchain and be happy. If you've decided you want to use the buzzword blockchain and you get some benefits from using that data structure, great. If you do need a public consensus, you maybe should do this. You should strongly consider doing something else. Take the Fortnite example. They have servers and they have a company, and you trust that that company is going to enforce the rules of the game correctly, because it's honestly an easier and better solution for many applications. But if you really think you need a public consensus, and you think you can get enough participants, and you have a mechanism of paying them to behave correctly so that the incentives are all aligned, then yeah, sure, you should use a public consensus on your blockchain. So, side note here, I was actually curious, how realistic is it to worry about a 51% attack? Because if someone evil manages to collect more than half of your mining nodes, it can then add whatever blocks it wants to it and say, just ignore whatever you add, because it's sort of like a network partition, right? Where you have a bigger half of the partition. And so to figure out what is a viable 51% attack, you need to know how big is the mining network right now, aka how many opponents do you have in this fight? And so this is public information, which is how many hashes per second is going on the blockchain right now. It's 122.1 terahashes per second as of May 7th. Okay, so how can we break this? Well, back of the napkin calculations, the peak hash rate right now in the Bitcoin blockchain is 120 million terahashes per second, consuming about 3.2 megawatts, which is a mind-blowing figure. So you can buy a blockchain mining computer. It's, for example, this one I pulled off the web, an Antminer S19 Pro, does 110 terahashes per second for only $2,600. Perfectly reasonable, right? To buy a computer just to compute meaningless hashes per second. So you need to buy about 1 million of these in order to take over the blockchain by getting up to 51% of the mining capacity. So it would cost you about $2.6 billion. So this brought to mind, who's got $2.6 billion in computers right now who could take over Bitcoin? So I actually used to be obsessed by this, because when I worked at Google, I was wondering if I was actually working in the biggest computers in the world. And for a long time, I was convinced I was using the biggest computers in the world. But you can roughly compute an upper limit on how many computers a company has by looking at their balance sheet. Because if they own property, they're legally required to list it under property and equipment net on their balance sheet. And so if you look at the balance sheets of various large computer companies, Google currently has $77 billion worth of stuff. Now that includes things that aren't computers. It includes the buildings they put the computers in, cooling systems, networking equipment, land, the buildings they put their employees in if they happen to own them and not lease them. They might own roads, they might own undersea network equipment, who knows? They own lots of stuff, but you know that they don't have more than $77 billion worth of computers, because that's how much stuff they own. So Google's at 77, Facebook's at 37, Apple's at 36, Amazon, well, they probably own some inventory too, so they probably don't have that many computers, but they're doing pretty well. Microsoft too. So the answer is, any of these companies could conceivably have enough compute power to win a 51% attack on their blockchain. So if they happen to have a rogue employee that decided they wanted to completely toast the company's business and take over all the computers, and they have the technical know-how to do so and stuff, they might have enough compute power to win a 51% attack. And probably not, because these are probably general purpose computers and not specialized mining hashing computers. But it's conceivable. then you have to ask the question as well, how good are these companies' defenses against such a rogue employee? And they're probably good enough to stop such a rogue employee. I would hope they're good enough to stop such a rogue employee. So it's probably not going to happen. But the fact that we're even talking about it being conceivable might give you some pause for reflection.
So there was a question asked in chat a little while ago, which is relevant to this, which is, do ASICs somehow solve this super hard math problem quickly and compromise the security of the blockchain? And my answer to that was, well, anybody who's serious about mining is going to have specialized hardware, or at least anyone who's very serious about it. But it only helps so much, which I think your example illustrates here, that it only helps so much. You need so many of these specialized ASICs to be able to actually mount this attack.
And your competition already has ASICs.
Mm-hmm.
Like the Antminer S19 Pro, that is a machine that's stuffed full of ASICs for doing nothing but computing hashes.
Mm-hmm.
And so I was thinking, like, Google has, I forget the public names of their chips in them, but they've got these specialized chips for doing AI in them. They've got ASICs in them. I don't happen to know how good those chips would be if you repurposed them for doing nothing but computing hashes, but they also have computers full of video card chips.
Mm-hmm.
And these processors also would be better at computing hashes than a simple CPU. So yes, the mining computers will win the race, but there also are tricks that can be played with general purpose computers.
A few people in chat are also mentioning banks and governments that they think would be able to conceivably mount this attack.
Yes, I don't know of any banks with billions of dollars in compute infrastructure. They certainly have impressive data centers, but I haven't looked that closely. And governments, I sort of put governments in the bin of, well, we'll never know, because the people who do know aren't allowed to tell us. And I would argue that, okay, from what I know of data centers, the NSA probably does, and NSA, CIA, the secret three-letter agencies of the US government, they probably do have some very large data centers, but I would be surprised if they were quite at the scale of like a commercial vendor like Amazon or Google.
And another point being made is not only the computers, but also the power consumption.
Yes. Yeah, no, it wouldn't be economical for these companies to do it. I'm assuming a malevolent attacker who's more than happy to waste Google's or Amazon's or Facebook's electricity if they could, destroy their entire business by repurposing the computers for something that makes no sense.
So we're actually well out of time now, which I'm not surprised by because we got started 10 minutes late. So we should probably wrap up.
Well,
although
luckily,
this discussion is very interesting.
Here's the last slide.
All right.
Blockchains are a great performance hack. Proof of work allows for a probabilistic public consensus at a huge performance cost, which you have to be willing to pay in order to use it. And it's kind of cool to learn about this stuff because it lets you understand cryptocurrencies. And I'd love for it to be useful in other domains, but it ain't there yet, in my opinion. There are some very strong opinions that people have who would argue otherwise. Sorry, I'm not one of them. And that's all I got. Also, I'm going to put a blatant plug in for if you want to see some more videos on other distributed systems topics that are way more simplified than what Lindsay's teaching you, you can check out my website.
All right. Well, thank you so much, Chris. I'm going to flip StreamYard back to showing your face instead of the slides. And then, let's see. Here we go. So thanks again. So let's say class is officially over at this point because we've already been here for so long. But just in case anybody still has questions, because this is a fascinating discussion, I'm wondering if any students in the class have more questions to ask. And either about blockchain consensus or about anything else that Chris has worked on. And so, okay, here's one question that just came up, which is, could you possibly explain the concept of proof of stake a little bit more? Because it seems less straightforward than proof of work.
I'd love to, but I'm not an expert in that area.
Okay.
I'm one of the people who, when I read about it, everything I read about it, everyone has a slightly different twist on the algorithm, and I'd have to go through and read the code to really deeply understand it, and I haven't done that.
Okay, here's another question. So the question is, suppose there's a fork. and node 1 chooses block A after its timer expires. Node 2 chooses block B after its timer expires. Is there any way for this fork to be resolved? Like, can you merge the branches of a fork, or is it just forked forever?
So yes, the fork will get resolved when the next block gets added, assuming it gets added to only one of the two branches and then communicated throughout the network. And at that point, the losing side, the block that was put on the shorter branch, will just get ignored by everyone. And so there is no merging of the transaction data. All the transactions that were in the block that got on the abandoned leg of the fork, abandoned branch of the fork, then have to be resubmitted to the system, and hopefully a miner will successfully get it in a block that gets published on the actual blockchain.
Okay. Merge was that wasn't actually the asker's term. That was my term. I guess I'm still using a Git metaphor to think about this.
Yeah. So yeah, I guess Git is interesting because it has the ability to merge, which requires human intervention.
Mm-hmm.
And so until someone comes up with an algorithmic way of merging arbitrary content, which of course they never will, you can't.
Well, you could come up with one, right? But it would suck, right? You could say, well, the merge is the empty string, right? But it would be
always
terrible.
Correct. Yeah, no, like there are merging strategies. Like the Coda file system is an example of a system where you needed merging. And I guess background, its Coda file system is a distributed file system where I can take my laptop and I can access files and I can unplug from the network and keep on changing my files. And then later when I replug into the network, it resyncs with the server and successfully, if the system works, uploads all my files to the server, even if two users had conflicting edits to the same file. Mm-hmm. And what the Coda file system does is it detects the cases of a merge where it can't merge successfully, say two people edited the same lines of code, and then it just bucks it back to the user and says, you're hosed now, buddy. How dare you and Lindsay edit the same source file at the same time? You shouldn't have done that.
Yeah, I was actually just reading about this the other day because for whatever reason, I had to read about systems that made you get permission in order to do a write. And so Coda was something that was referenced. Mm-hmm. Okay, one final question. So do you see any potential for government regulation of Bitcoin, like or blockchain? Like, for example, the student is suggesting, for example, NIST defining a common blockchain approach, and possibly even incentivized in a way that you don't have to have a ridiculous amount of hardware in order to participate. This might be a question more for a political scientist.
Yeah, I would argue. I'm a technical person, so I can't be authoritative on this. But my personal reaction is no, it can't work. And the reason it can't work is because we already have ways of government regulated exchanging value between humans that work really well. That's called currency. Like that's what money is. It's a government mediated exchange of value where if something goes wrong in a transaction, you use a government median resolution technique called a lawsuit or a war in terms of international relations. And it works really well for most applications. And so the whole purpose behind blockchains, cryptocurrencies, not necessarily blockchains, is that we can exchange value between people without involving a higher authority. And so if you bring the higher authority into it, you'll be like, well, why did I do that? What's the purpose?
Right. If the whole point was not to participate in government-controlled currencies, then to put the government in charge again seems counterproductive.
It would get you back to where you were in the first place with a solution that is, well, quite frankly, better for most applications.
All right, we're far over time now. And so thanks to everybody who stuck around and asked questions right up until this end. But I think let's thank Chris for giving a great talk. And
I'm sorry for going over time.
Oh, well, I mean, we had a great discussion. And I interjected with lots of questions, so I'm not surprised. Please check out distributedsystemscourse.com for Chris's online course. And thanks again. See you all on Friday.
And thank you for having me.
All right, thanks, Chris. Take care.